Alright, welcome to another AQA chemistry video. Today I'm going to be doing the ideal gas equation and empirical and molecular formula. So, there's a two-part video actually, but I'm going to do it all in one because I've separated. I think you can just do both topics at the same time and they kind of entail. And I've got a question in here that relates to both topics, so we'll do that at the end. So, most gases obey a simple law known as the ideal gas equation. It entails the relationship between pressure, volume, moles, and temperature of a gas. The ideal gas equation is pressure times by the volume, which is equal to the number of moles times by the gas constant times by the temperature. I'm not sure if you have to remember that from GCSE. I don't know if they do that in GCSE. I don't think they do it in GCSE, but that is the equation. Pressure times by the volume equals the number of moles times by the gas constant times by the temperature, right? How I remember it always is PV equals nRT. That's really memorable. That's how I always remember it. PV is equal to nRT. And this equation can be used to calculate any variable in the equation as long as you know the other three variables. So P, V, N, and T are the variables. So R is a constant, so it's always going to be the same as 8.31. And don't think you have to know the units for it, but it is 8.31. It's actually 8.3139, so on, so on, so on, so on. But you round it to 8.314. But from what I've seen in the exam, how I did it in exam, it was always 8.31. It was always three significant figures, but yeah, the 8.31 is usually what you have to remember. The importance of the units. When using the ideal gas law, it's important to make sure that you're using only SI units. And this is where most people lose marks during doing these questions. These questions are usually 3 or 4 marks. I mean, not too many marks. It's just rearranging the equation, usually, these questions. Unless you, I mean, with this question, you might have to work. You only really need, when it says that you only need 3 other variables, because R is always given to you. You really need to do is the temperature, the temperature, the pressure, the volume. Because the moles, you can actually work that out from another example. They might not give you the moles directly, but you can work out the moles from, if they give you, because moles equal to mass of the MR, so if they're giving you the mass and the MR, then you can do that, or you can work out the MR. Concentration equals the moles of the volume, so if they give you concentration and volume, you can work out moles. So this is from ways to work out moles. So pressure, volume, and temperature are things that you have to at least have or at least use to work out. But the place where most people lose mark is actually the units, because people forget that it's in pascals, not kilopascals. In the questions, usually they give it you in kilopascals. We have to convert that from pascals to from kilopascals to pascals, which is just times 10 to the power 3 or times about 1,000. It's in meters cubed. Usually in chemistry, you get decimeters cubed, but 1 decimeters cubed is 1. If they give you 1 decimeters cubed, that's equal to 1 over 1,000 meters cubed. Yes. 1 over 1,000 meters cubed. Right. So because usually you have in chemistry you usually get in decimeters cubed or centimeters cubed, and 1 decimeter cubed is equal to 1 over 1,000 meters cubed. Right. The temperature must be in Kelvin. That's fine. And these units are scientific standards, and they're related and allow for values to be easily understood. Using different units will give you a wrong answer. So make sure that this is where most people get using mark. You usually only lose 1 mark because it's just timesing it by 1,000. So, but that is where I mean, if you use the mark, you can use the mark from lose a mark for giving the wrong, not converting it, and then you lose another mark for giving the wrong answer at the end. So you could lose two marks at least minimum. So yeah. So for example, the question they'll give you is, for example, the pressure of 0.8 moles of a gas is 100 kilopascals. Also, 1 times, it can also, 100 kilopascals is the same as 1 times 10 to the power 5 pascals. At temperature of 398 Kelvin, what's its volume? So we always write out the equation, PV is equal to nRT. We rearrange the equation because we're trying to find the volume, right? We're trying to find the volume in this case. So that's equal to nRT over P. Our moles is 0.8, so 0.8 times by our value for R, which is 8.31, times by our temperature, which is 498 Kelvin, all over 100,000 pascals, or 10 to the power 5, same thing. And our volume is 0.0265 meters cubed. Notice how it's three significant figures, because all of our values in the question, the minimum one is three significant figures, three significant figures, three significant figures, and three significant figures. So our answer's minimum significant figures must be 3. I'm going to skip this question. I'm going to do this question at the end, but I want you to try and do this question here, right? Pause the video now and try to answer the question. Alright, so this question says 1 mole of a gas is a volume of, I assume you've already done the question now. 1 mole of a gas is a volume of 1 litre and a pressure of 100 kilopascals at a temperature of 12.028 Kelvin. What's the value of the gas constant? Well, you already know technically, if you already know what the gas constant is, you already know the answer's already, we already know the answer is 8.31, right? Because we know the gas constant is always 8.31. Because it's constant, no matter how many value, the value, it's a constant because whatever we have in our values they always make it 8.31. And if the value is not 8.31, it means there's something wrong, because it's always 8.31, no matter what the question is. But let's just see, but we have to answer this question as if we don't know how to get to 8.31, or we don't know what the answer is. So about how to get to 8.31, we would do PV, always write out our equation first. PV is equal to nRT, right? And I should probably write that bit closer together, make it sound like there's a gap. PV is equal to nRT. We're trying to find R, right? So rearrange the equation. So R is equal to PV over NT. Yes. And our pressure is 100,000. I always made this mistake during questions. Sometimes I already know that's 100,000, but they actually do like it when you actually say, pressure. Sorry, keep doing that. Pressure is equal to. They actually like it when you show that you've converted your answer. So try and do this. So 100 times by 10 to the power 3 or 1,000, 100,000. Because I always put down. I already know that 100 kilopascals is 100,000 pascals, but they really want you to show you that it's 100,000. So 100,000. The volume is 1 litre. So that's 1 litre is 1 decimeter cubed, which is 1 over 1,000 meters cubed, which is equal to 0.001 meters cubed. So times by 0.001 meters cubed over the moles, which is 1 mole. So we can just do that 1 in our calculator. We didn't really put that down. And our temperature is 12.028 Kelvin, right? I could just cancel those out, but let's just write out. No problems anymore. Let's write out what it is. 100,000 multiplied by 0.001 all over, I'm not going to write that one, but 12.028. And you see here, that's our answer, 8.31. That's 8.3139. I would leave it as 8.31 because the most amount of significant figures that we get from our question is, the least is, I'd say, 3 significant figures. Is it 4? 3. But it's 8.31. They probably, in this question, probably specify it, but I'd go for 8.31. But it's 8.314, but they round up. So in reality, it's a much longer number, but 8.31 is enough. So R is equal to 8.31. I don't remember the units for this, but I don't remember them actually really caring about you having the units for this question, for the gas constant. But they'll usually have it there, and if they can't specify it, you can work it out by just looking at what you have in your equation. So 8.31. I'm going to go into the empirical molecular formula now. The empirical formula is the simplest formula of a compound you should know from GCSE. The molecular formula gives the number and types of atoms in a compound. The empirical formula is the simplest whole number ratio of atoms in a molecule. For example, ethane, the molecular formula for ethane has 2 carbon atoms and 6 hydrogen atoms, and therefore that's 2 to 6. So the empirical formula would be, if it's the simplest ratio, would be CH3, right? CH3 here. I should probably put that in capitals, really. CH3. Okay. The molecular formula is the actual number of atoms of each element in a molecule. It's always a multiple of the empirical formula. For example, ethane has 2 carbon atoms and 6 hydrogen atoms. C2H6 is the molecular formula of ethane. This is 2 times this empirical formula, as you see here, as we said before. Experimental determination. The empirical formula of a compound is often very easy to determine experimentally. For instance, you could combust a hydrocarbon and find that you get twice as much water vapor as carbon dioxide. You can combust a hydrocarbon and find that you get twice as much water vapor as carbon dioxide. This would tell you that its empirical formula is CH4. Remember, H2O contains 2 hydrogen atoms, right? A molecular formula is relatively difficult to determine experimentally, so this is why we only do it that way. All right, so molecular formula is shows the actual number of, just a reminder that molecular formula shows the actual number of atoms which make up a molecule, not the simplest ratio. So if I've got glucose here, which has the formula C6H12O6, quite an easy one for you to do, but what's the empirical formula of glucose given that? So beta glucose doesn't really matter, but what is the empirical formula of glucose? I'll give you a couple of seconds, pause the video and now answer it. Alright, well, you can already see from here, C6H12O6, the simplest ratio, CH2O. That's the simplest ratio there. Right. I want to go to this question here. Actually, I want to go through this part here. Right. This is going to be, I was going to go through this one here. So obviously Pascal's, there's times that by 10 to the power 3. But when you're doing units, one thing that some people mess up on is usually they could give it to you as decimeters cubed or a liter, but they could also give it to you your volume as centimeters cubed. And a lot of people make this mistake, and I made this mistake before, but I learned it anyway. But you probably won't make this mistake. Going from centimeters cubed to meters cubed is obviously it's not the same as just going from times 10 to the power 2, because people just know that going from centimeters to meters is 100 times by, going from centimeters to meters cubed would be, some people would think that going from centimeters cubed to meters cubed would just be divide by 10 to the power 2, because centimeters, to go from centimeters to meters, you're dividing it by 100, right? But it's not as simple as that, because it's a volume, so you're cubing that volume. So how you need to understand it is going from centimeters to meters, right? You're dividing it by 10 squared. But now it's that's from centimeters to meters. Now, if you're going to cube that, if you're going from the volume, you would cube your 10 squared. And now when you're cubing an index number, you would multiply the indices here. And therefore, you're dividing it actually by 10 to the power of 6, because 2 times 3 is 6. And there you go, you divide by 10 to the power of 6. Or if you're going from meters cubed to centimeters cubed, it would be times by 10 to the power of 6. But if you're trying to get to meters cubed, so you divide by 10 to the power of 6. Okay. Now after you've learned both sections of that, I want you to go for this one question here. Is combustion of a straight chain alkane is in a sealed container at 298 Kelvin and 100 kilopascals of pressure produces 0.1 meters cubed of carbon dioxide and 0.125 meters cubed of water. What's the empirical formula of the alkane? Pause the video now and try and answer the question. Alright. I'm assuming that you've tried to answer the question now. So with this question, you need to understand what's going on here. So the first, this is a combustion reaction. And whenever I see all these questions, I see a lot of numbers here. What I do is I always do a checklist. I write out my equation first, right? PV equals nRT. and I say they want you to work out the empirical, but what are they actually giving you? Giving you the pressure. I want to cancel. I want to see what them, because I from this reaction I can always see that I can see volume, I can see the temperature, I can see pressure. In my head I'm thinking it's related to PV equals NOT. That's what your brain should automatically think. When you see those values together, you know it's something to do with the PV equals NOT equation. What are they giving? They've given you the pressure, right? They're giving you 100 kilopascals of pressure. If you want to have the answer, if you've answered the question, you just want to go to the answer, you just skip to the end of my explanation and just go straight to the answer. If you really just want the answer, but if you want the explanation, you're just struggling to answer the question, I'm going to try and explain to you, right? So they've given you the pressure, they've given you the volumes, they've given you volumes really, they haven't given you the moles. So maybe that's what they're saying. R is always just, you should know that temperature they're giving you. So they want you to work out the moles. Clearly, they want you to work out the moles. And it makes sense. If you want to work out the empirical formula, you need to know the ratio of the amount of moles to one thing, to another, to one atom to another atom, in order to actually get that empirical formula. So what can I work out from here? So the pressure is the same because we're using it's all in the same reactions. The pressure will be the same for both. The volume, they've given us separate volumes. R and T, temperature is the same, and RC is just a constant. So I'll just rearrange this equation, and if I want to work out the moles of, let's work out the moles of carbon dioxide first, right? So for moles for both cases would be N is equal to PV over RT. And the moles of carbon dioxide, pressure, remember it's 100,000, not 100, so the pressure would be equal to 100 times 10 to the power 3 or 10 cubed, 100,000 times by the volume, which is 0.1, because they've already given it to you in meters cubed, so that's actually quite useful, over 8.31 times by the temperature, which is 298. And then our moles would be 10,000. I'm just cancelling it out. 10,000 over 8.31 times by 298. 10,000 because there's 100,000 times by 0.1 there. 4.034. Let's just call it 4.038. Right? Call it 4.04. Right? That's the amount of moles of CO2. The moles of H2O would be, by the way, when you're doing this question, you do it much faster than the way I'm doing it. I'm just trying to explain to you every single part here. But same thing really. We already know it's going to be 100,000 here times by 0.125, that's the only difference, and then multiplied, also all over 8.31 multiplied by 298. It makes sense that it's 298. This is just room temperature. $100,000 times by 0.125, and that's 5.05, let's say, all right? 5.05 moles. Make that better, 5. That's a terrible 5. 5.05, and you should put the value here, mole. Right. The question was, what's the empirical formula of the alkane? What's the empirical formula of the alkane? Well, what I forgot to do in this question is, what I should have done at the start is my bad. I actually put down, what I would have actually done is put down the equation, right? So we have the alkane, let's call it alkane X, right? We have an alkane of X, and this is, you're producing, it's a combustion reaction, so you have oxygen. It's we're only producing carbon dioxide and water, so it must be a complete combustion. So X plus O2 goes and forms CO2 plus water. Alkanes would only have hydrogen and carbon and hydrogen. So we care about the moles of carbon and hydrogen. We know that in this case, because we're only forming CO2 and H2O, we know there's only going to be we know that the amount of carbon, right? the oxygen don't care about, that's just going to be related to that. But the number of carbon is the same as the number of moles of carbon in the alkane. And number of hydrogen will be the same number of moles of hydrogen also in our alkane. So there's 4 moles of CO2, i.e. that means there's the same number of moles of carbon. There's only 1 carbon atom in CO2. So there's our alkane there's approximately 4 moles of carbon in our alkane. There's two moles of hydrogen per water molecule, because there's 2 hydrogens per water molecule, so there's double that. There's 5 moles of H2O, therefore there is approximately 10 moles of hydrogen. Therefore, our alkane is C4H10, which is butane. But we're not done yet. The question was, what's the empirical formula of the alkane? And the empirical formula would be the simplest whole number ratio, which therefore means that the empirical formula is C2H5. That's the empirical formula of this compound. Hopefully this video was helpful. I know I'm still working on making these videos better, but bear with me. I'll try and make these videos better, but that's the end of the video. Bye.